So, we were discussing diffusion in other coordinate systems. So, we looked at we were halfway through steady diffusion in axisymmetric coordinates. So, this is steady diffusion in axisymmetric coordinates. I will kind of quickly draw the figure here, the domain and the discretization, so that it can help us formulate the problem. So, unlike the 2 dimensions, we have now an axis about which this will be revolved, right. Essentially, there will be this is an axis of revolution, and then we are talking about delta theta equals 1 radian, right. So, all these cells that we have are swept in the theta direction by 1 radian, okay. That is what we have, and we also have the cells, that is the primary cell P, east cell, west cell, north and the south, and the distances we have are delta x in the x direction, delta r in the r direction, right. We also have the distances between the cell centroids, those are how much? Delta r north and delta r south, right. And the distances in the x direction between the cell centroids are how much? They are delta x east and delta x west, correct. So, those are the metrics we have, and then we also know the radii, right. The radii are Rp or Re, right. This is Rp and so on to Rn, R south and so on, right. So, we have the faces which are between the cell centroids, those are east, west, north and south, right. And then what about the area vectors now? For these cases we have, we said AE bar is how much? AE bar is delta r, okay. So, delta r has to be swept by 1 radian in the along the theta direction. So, that should be how much? Re times 1 radian, right. Re would be same as Rp, right. So, essentially I just put it there because it is east, right. That is AE bar. And what about A west? Minus delta r west 1 radian, okay. What about other area vectors? So, what about A north bar? Rn times 1 radian times delta x, and A south would be minus R south 1 radian delta x, okay. So, and what about the volume, delta volume for this cell? Rp, okay, times 1 radian times delta r delta x, okay. So, that is your volume, okay. And now we are talking about the unit vectors. Unit vectors are Er hat in the r direction and I hat in the x direction. We have to also of course define what is our nabla, right. That is our del operator. Del operator for axisymmetric coordinates is Er hat partial r plus I hat partial x, okay. That is our del operators. Then we would go ahead with the governing equation. Governing equation is what? Del dot k grad T plus St equals 0, right, okay. So, we used temperature here instead of phi to not get confused with the angle theta, right. We also have theta there, which is for the azimuthal coordinate, okay. Now, if you apply Gauss divergence theorem and then integrate this on a finite volume, apply Gauss divergence theorem and then write the discrete form of this equation, that would be what? That would be sigma f k grad T f dot A f bar, right, plus if you also say that there is an average value for St bar, which we are modeling using a linear source term, then this would be Sc plus Sp Tp times delta V equals 0, okay. That is fine. Then what about the faces? The faces are the east, west, north and south. So, if I calculate what is k grad T f, this would be how much? K f times Er hat partial T partial R on the face f plus I hat partial t partial x on the face f, right. That is our k grad t f vector. Now, what will be then our k grad t e dot a east? A east is, oh sorry, I think I missed the unit vectors here, isn't it? Delta r re 1 radian times which direction is it pointing in? I hat, north is in er hat, this is I hat and this is er hat, right. Those are the unit vectors. Now, what about the evaluation of this quantity on the east face? K grad t east dot a east bar, how much would this be? So, which term survives? Only the I term, right, because it is only in the x direction. So, only the I term survives, and how much would that be? K east times RP, okay, that is, I would still write it as RE, okay, KE RE, what else? Delta R partial T partial X on the east face, right, that is what we have. And then similarly K grad T west dot A west bar would be how much? Would be a minus, right, that would be a minus K west R west delta R partial T partial X west, okay. And then K grad T north dot A north bar would be how much? Would be K north times, only the first term survives now, the ER hat term survives. How much is A north? Rn times delta x. So, this would be Rn times delta x times partial T partial R on the north face, right, and then we have ER dot ER inner product, okay. Then K grad T south dot AS bar would be minus K south R sub S delta x partial T partial R on the south face, okay. Of course, now we can apply a linear profile assumption for the variation of temperature between the cell centroids and evaluate these gradients on the faces, right. For example, dou T dou x on the east face, we can write it as T east minus Tp by del x E and so on, okay. And then we will use those relations to substitute back in here, right. We will use this, substitute back into this, and then rearrange the terms, right, and then we get our favorite equation, that is AP Tp equals sigma A and B T and B plus B, okay, out of which what is A east now? A east is K east R east delta R upon del x E, right, fine, okay. A west K west R west delta R upon del x W, right, and A north K north R north delta x upon delta R north, and then A south would be K south R south delta x upon delta R south. Of course, what is AP? AP would be east, west, north and south, and what else? AP term minus SP delta V, that is nothing but RP delta R delta X, right, delta R delta X. And then what is B? SC RP delta R delta X, right, that is all, fine, okay. So, essentially everything else remains the same. You can of course apply boundary conditions as special cases on the boundary faces whenever it is given, and we can go ahead and solve solutions, you know, for these axisymmetry problems, okay. Questions till now? So, given let us say any other 2D geometry, you will be able to do it this way, right. The steps are basically the integration, then the Gauss divergence theorem, then calculate the areas, and then find out what will be the resulting equations, right, using a linear profile assumption and so on, right. So, that is easy. Questions? No? Okay, clear, very good. Alright, so that kind of finishes the diffusion equation, steady diffusion equation in other coordinate systems. We will kind of move on to now to unsteady diffusion. Okay, then we will come back to steady diffusion for unstructured meshes. Okay, after we finish unsteady diffusion, and also we will look at the stability criteria, truncation error, all those things, and then we will come back to unstructured meshes after we finish all these discussions. Fine. Okay, then let us move on to the discussion on unsteady diffusion. So, this is unsteady conduction equation. All right. So, how do we obtain unsteady conduction equation? Essentially take the general scalar transport equation and knock out the which term? Remove the convection term, right? That is all. Essentially what was the general scalar transport equation? That was partial t rho phi plus del dot rho u bar phi equals del dot gamma grad phi plus s phi, right? Up till now we have set everything on the left hand side as 0, right? We knocked out the unsteady term and the convection term, and we were working only with the del dot gamma grad phi plus s phi. Now we will only set this term to 0, right? As a result, we have unsteady diffusion equation. Okay, through this unsteady diffusion equation, we are bringing in one more property of the fluid. What is that? Or the whatever the material we are considering, density, right? Up till now we have only gamma. Now we are bringing in density. Rho is coming into play through the unsteady term. Okay. Then what all do you need to solve this problem? You would need, of course, the boundary conditions, right? You would need the boundary conditions. What else do you need to solve this problem? You need an initial condition because you have a time derivative in there, right? So, essentially you would need an initial condition. Initial condition will be specification of the dependent variable, that is phi. Do you need it specified at t equal to 0, right? That is your initial condition. And where do you want it to be specified? Everywhere in the domain or only on the boundaries? Everywhere. Essentially you want it for all x and all y, right? You want a condition to start off with. That is your initial condition, and then of course you have boundary conditions which are on the specific boundaries, from x equal to x constant and y equals to y constant, and you want it for all time, right? You want so many of these boundary conditions also to work with for all the combinations, okay? For all x, for a y equal to y constant, for all y, for all x equal to x constant, and so on, okay? So, you would need all the boundary conditions and the initial condition. Now, what kind of an equation this is? Is it still an elliptic equation? Let us say we say gamma is some finite value, okay. So, there is a lot of diffusion in the problem. What kind of, what type of equation is this? What type of PDE? Is it still elliptic PDE? No, this is now, what is the, it might most likely it will be either a parabolic or a hyperbolic, depending on the amount of diffusion we have. Let us say it is a parabolic, say that there is a lot of diffusion happening because it is unsteady conduction. So, this is a parabolic type of equation, okay. Fine. Then what we need to do is, up till now we have been only integrating the equations on a particular control volume, right? That is the first step in finite volume method. Now we have this time derivative, okay. So, in addition to integration on the volume, we have to also integrate along time, right? We have to go in steps of some delta t, right? We start off with let us say some time t or some time 0, and then we move on to t plus delta t, okay. So, essentially we have to integrate on time and on space, right? We have to do both these steps. So, that means if I take the governing equation, which is this equation, okay, and integrate both on with time as well as space, then what we have is integral t to t plus delta t, okay, and integral on the control volume. The first term is partial t rho phi dv dt, right? That is our unsteady term. I am integrating both on the control volume, also in time, right, t to t plus delta t. So, I can also shorten this and write, instead of integral t to t plus delta t, I can also write it as integral over delta t, integral over delta volume, right. We understand delta t is basically we are going from some time t to the next time t plus delta t, okay. Okay, what else is there on the left hand side? Any other term? No other term. We have to move to the right hand side. What is there on the right hand side? integral delta t, integral delta volume, we have del dot gamma grad phi dV, right, plus integral delta t, integral delta volume S phi dV dt, and of course, there should be a dt here also, right, dV dt. Fine. So, we obtain an equation. Now, let us kind of look at each and every term, okay, one by one. Let us look at term by term. Okay. So, let us take the unsteady term, that is the first one. So, that is the unsteady term, and if I assume that these integration commutes, okay, I can rearrange this integration as integration over the delta v and integration over t to t plus delta t partial t rho phi dt and dv. Okay. I have rewritten it assuming that the integration can commute here. Now, what is the integration of the inner term here? Partial t rho phi dt, integral of this thing, what would be this quantity? Rho phi, right, this is essentially rho phi. Do you have limits for integration? Yes, you have. So, essentially it will be rho phi at t plus delta t minus t, right, into delta v. Of course, that is there, you have to sum it for all the small volumes you would get. So, this is essentially rho phi, right, at t plus delta t minus rho phi at t integration over the each of the control volumes that you would consider. Okay. Now, again I make an assumption which is rho phi is for a small control volume, right. So, I will say that this for the particular control volume, the cell centroid value of phi p prevails over the entire cell. Okay. Essentially that means I can rewrite this as, and I have an integration over the particular cell, right, or the particular control volume. So, I can rewrite this as rho phi p at t plus delta t minus rho phi p at t. Okay. So, this is basically the cell centroid value of phi p, okay, and I am integrating on the control volume delta v. So, this would be times delta v. Can I write this? Yeah. Okay. Similar to what we have done for the source term, right. We are calculating the average value, which is the cell centroid value, and then we say that that prevails over the entire cell, right. The small control volume, instead of integrating, you have a constant value over the entire cell, some average value, and then we are multiplying with the volume. Is that correct? Is there a dt multiplying also? No, there is no dt, but there is delta v multiplying it, right. Is that correct? Fine. Okay. Now, I will kind of switch to a simpler notation. I would like to represent t plus delta t, instead of t plus delta t, I would like to write it as 1 superscript 1 and t with superscript 0, okay, indicating that 1 is the current value, 0 is the previous time step value. Okay. So, essentially this is the current value and this is the previous time step value. Okay. Yes. Yeah, for rho as well. Okay. Essentially rho phi p as such, I am assuming that the density is not changing. Let us say if you have an incompressible flow or something. Okay. I am assuming the density is constant, otherwise it will be rho p as well. Okay. It will be rho p phi p, fine. Okay. So, fine. Then let us move on to the next term, that is what was the next term? Diffusion, right, that is this term. Okay. So, that is, if I write it down, it is integral t to t plus delta t, integral all the control volume del dot gamma grad phi, right, is that correct? Del dot gamma grad phi dV dt, but we realize that this term is on the right hand side of the equation. Okay. We are done with the left hand side, there is only unsteady term, we have come to the right hand side. This is important because when we calculate the coefficients, we should be putting them with correct plus minus. Okay. All right. Now, what do we do here? Essentially, we can again invoke Gauss divergence theorem convert this volume integral into surface integral and with a discrete summation. Okay, if I do that integral t to t plus delta t, I can replace this entire thing of here with the already known value, that is what? Summation on all the faces, right. So, this is on all the faces, let me write it as SS, okay, and what would be this value? Gamma grad phi on the faces dot A, right, A for the faces, okay, A bar, fine. This is all the faces that make up the control volume, fine, times what do I have? dt, right, okay, fine. Any questions till now? No questions, okay. Now, what we have done is we have to, so of course, this grad phi, we will assume that it is again a linear profile assumption between cell centroids. Now, we have to do something similar here. Now, so essentially we have to carry out this integration. We have this term in the parenthesis that has to be integrated over this time step of delta t, right. So, what we say is that we again make use of a linear profile assumption in time for this quantity. Okay. So, I am making a linear profile assumption in time for this particular quantity in parenthesis. Okay. That means similar to the interpolation of gamma, you remember interpolation of the diffusion coefficient on the faces, we had some factor, right, we had some Fe times gamma p plus something, right. Similarly, I have two quantities here, one is this gamma grad phi f dot af, where the sub f stands for the phase. Okay, we have this value at t plus delta t, right, and we have another value which is gamma grad phi f dot af at t, right. I have these two values. So, let me write it this way, let me write it t on the left hand side and t plus delta t. So, I have two values, right. Of course, this is again a summation, right, on all the phases, that is fine, right. We have these two values at different time steps at t and delta at t plus delta t. Okay. So, if I were to draw it, essentially I have this is my gamma grad phi f 1 dot af, and then this is my gamma grad phi 0 f dot af, right. I have two values and I am considering this to be some kind of a linear variation between these two values. We still have the summation, right. We are talking about time in this direction, right. I have this, that means I can write this with some factor, okay. That factor I would like to call it as f, okay, and that f is an interpolation factor which is different from this f we have here, okay. So, if we have an interpolation factor f, I can calculate this entire quantity as an interpolated value, right. That would be how much? So, whatever is there in the parenthesis, that would be f times this quantity that we have, that is gamma grad phi 1 f dot af, right, plus 1 minus f times gamma grad phi 0 f dot af. Is this okay? Of course, we have it for all the faces, the summation is there on the faces, right, where this f here is my interpolation factor, which I have not defined yet, okay. It is some linear interpolation factor. It could be anywhere between 0 to 1, right, fine, that is this value. I have introduced some kind of a linear interpolation between 0 value and 1 value, right, and I would say this is the value of the term that is there in the parenthesis here, okay, fine. Now, what will be this integration with this particular interpolated value? What will be the result of this integration? That is nothing but integral t to t plus delta t, and we have this big expression that is f times gamma grad phi 1 plus 1 minus f times gamma grad phi 0 dot af, right, that is interpolated value times dt, right, that is what I have, okay. Let me write it down. So essentially the integration would be integral t to t plus delta t. What I have is f times gamma grad phi f dot af plus 1 minus f times gamma grad phi 0 f dot af. This is again summation on all the phases times dt. Is that correct? Question, yes. Yeah, I would just assume that the interpolation factor is, this interpolation factor is in time. Okay, so maybe shall I use G or something instead of F? Would that make it clear? The sub F is basically phases. This is phases. Summation sign is inside. It doesn't matter, isn't it? You want it to be inside? Okay, I'll put it inside what? Inside F or something. Okay, I'll put it there. It doesn't anyway matter. Okay, I'll rewrite it. Fine. Essentially, this is summation on all phases, right? Times F, right? And then this is summation on all phases times 1 minus F times dt. Is that correct? Fine. Essentially, we have some interpolation factor F, which could be some value between 0 and 1. It could be 0.2, 0.5, whatever, right? So, we have this quantity gamma grad phi dot af, which is being evaluated to some value at t, some value at t plus delta t. We are trying to calculate some interpolation between these two, and then we have some value. Okay, now that value is what we have to integrate over this dt, right? Okay, now I have interpolated this value, right? Why do I think I made a, yeah. So essentially, what will be this integration now? I have some value that I have already interpolated, so I can rewrite this integration as this times the constant delta t, right? So this is nothing but f times sigma gamma grad phi f1 dot af plus 1 minus f times sigma gamma grad phi f0 dot af times delta t. Is that correct? This is some constant value, right, which I am integrating over the entire delta t, t to t plus delta t. Fine. F, what is F dependent? F is an interpolation factor that kind of determines the kind of time stepping scheme you want to use. We will come to that little later. As of now, F is some interpolation factor. Remember the interpolation of gamma, where we have two particular cell values, it would go from one cell to the other cell, right. So, similarly, F is something that we would decide based on the temporal scheme we want to devise. Okay, as of now, I would say F goes from 0 to 1 and depending on the value you choose, you will get something here. Okay. As of now, of course, we do not know what is the value of 1. For example, this term I have written down, but I do not know this value, right, because 1 is something that I have to calculate from 0, fine. So, as of now, I would say F is some factor which will relate these two. So, how does this term look like if we were to integrate? Let us say F is 0.2, right, F is 0.2. What will be the value of this integration? How does it look on this graph? Maybe that will make it a little more clear. So, I have this graph here. If I take F equals 0.2, what will that be? 0.2 of this guy, right, or 0.2 times delta t is what I have, right. It will be like a step, isn't it? You are calculating 0.2 times this quantity, right, times delta t plus 0.8 times this quantity times delta t, right. It is kind of going to cover the area under this curve in 2 steps, right. Okay, I would leave it for you, fine. Then we are also little lazy to write, so we are going to also drop this index 1, which is for t plus delta t. Okay, so I would say I would drop the index superscript 1, I would drop it. So, if there is a superscript 0, that is for previous iteration. If there is no superscript, that is for current iteration. Okay, I would, so we can save some writing, fine. So, that is basically this entire thing rewritten, right, f sigma gamma grad phi f dot af plus 1 minus f times sigma gamma grad phi f0 dot af times delta t, right. Okay. So, 1 is the present value which is not written anymore. All right. Then what is the value, let us say, of gamma grad phi east dot a east? How much would this be? Let us say if we have a 2-dimensional problem and we are also back to a Cartesian mesh, okay, in 2 dimensions. We have done this, right, in diffusion. What will this be? This will be some gamma east, A east is let us say delta y times del x e times phi east minus phi p. These are all evaluated at 1, which we are not writing, right. Okay. Now, what about the similarly, what about gamma grad phi 0 dot a e? That is basically would come from this term here, right. This will have 4 terms and this will have 4 terms, right. How much would this be? This will be, it will be the same, but there is one difference, phi 0, right. These are all evaluated phi 0 instead of phi 1. Okay. So, that means gamma east delta y by del x e times phi e 0 minus phi p 0, right. Okay. So, what is our objective? We are doing all this superscript 1, superscript 0, all these things, but what is our objective? Given a time level t, right, or an initial condition, we want to calculate phi at the next time level. Essentially, what is the unknown in this case, in these cases? Everything that superscript 1 or no superscript, right, that is the unknown, and everything with superscript 0 are all known, and we have the initial condition to begin with, right. Fine. Okay. Okay. What is the other term that is remaining in the equation? The source term, right. We have the source term which needs to be also considered. So, that is the source term. So, we will use a similar to the diffusion, we will also assume that the source term also has a linear variation in time. Okay. So, essentially that means integral t to t plus delta t over volume, what is that we have? SC plus SP phi p, right. This is what we have. So, I would write it as just the SV dV dt, right. That is what we have in the original equation, and this is nothing but integral t to t plus delta t SC plus SP phi p. This is the average value times delta V dt, right. That is the value of the source term. Now, we again use a interpolation factor f, and we would write this as f times SC plus SP phi p, evaluate 1, right. Okay, I will put the 1 outside, okay, because SC could also be dependent on the phi p, right. As a result, that could also change. So, I will put it on the top. Then we have plus 1 minus f times SC plus SP phi p 0, right, and both of them have what is the multiplication both of them have? Delta V times delta t, okay, where we have not defined what is f still, okay. F is some linear interpolation between 0 and 1. If I choose a scheme, okay, so the question is, will the f be the same between the source term and the diffusion term if we choose a scheme? Now, that is something usually when you choose a particular scheme, the same interpolation will be applied for source terms and diffusion terms, okay, but it need not be the case. For example, right now we do not have convection terms, right, say, and let us say you realize that the source terms are highly nonlinear. As a result, you may want to choose a different f for source terms and a different f for the diffusion term or for the convection terms. That is very much possible, okay. But if you do it that way, then or in either case you have to specify how did you choose the time discretization, okay. What is the f value you have used for diffusion, for source terms and for convection term has to be specified when you solve any problem. Many a times it is probably required that you choose different f for different terms in the equation, okay. That means you are kind of controlling what factors would come into the equations. We will come to that once we define what is f. We will see how these terms will kind of come into play. Okay. Now, we will also see that depending on how you choose f, these terms would either go into the b term or they would either go into the phi p term. Okay, that also happens. Okay, that is there. We will come to that. As of now, any other questions? Yes. Oh, nothing. I just, instead of writing 1, I am just lazy and not writing 1. That's all. Okay, if I don't write 1, just make sure just think that that is actually the current time level. That's all. Okay, so here I have put it because for the sake of completeness. Okay, that's all. Yes. 1 is something that is unknown. 0 is something that is known from the previous time step. Other questions? Yeah. Change in the diffusion coefficient between time steps. Okay, so I am not considering the change in diffusion coefficient in time. Okay, that means essentially gamma is not dependent on time. Okay, it's only dependent on space and the could be dependent on phi as well. Okay, so if that is the case, then gamma also has to have a superscript of 1. Okay, if that is the case, just like rho. Okay, I am not considering at the moment. Fine. Other questions? That can be done, isn't it? It doesn't. It will be the same. You just have to put 1 and 0 on the superscript for gamma, like we have done it for the source terms. That is possible. Other questions? Clear what we are doing with delta t? Yes. It should be still be known because gamma usually for a problem diffusion coefficient would be known. So you have a substance which is which has a time varying diffusion coefficient, then it would be known, right? Just like you know the value of gamma as a function of the dependent variable phi, you would also know how it behaves with time. Density the same thing. You should know what is the material density, right, depending on the other properties. Yes, I have here I have kind of neglected it, but otherwise this was already 1 and 0. Yes, I mean what his question is essentially I did not put 1 here and 0 here. His question was why did I not put 1 here and 0 here, but otherwise they are considered. Okay, so I have assumed that gamma east is there. Okay, but these will eventually come into the coefficients. So at that point we may need a different set of coefficients for these, right, because now they are the same. I would call the coefficient as A east for both phi 1 and phi 0 because they are the same, right, but otherwise they would not be, right. Other questions? No? Okay. Now then we have this big task ahead of you is you have to now combine all these things and tell me what will be the equation. Okay, AP phi p. So or else you can help me write it. Probably you can take a look and help me write it. So essentially let's first consolidate the equation. Okay, what is the consolidated equation? On the left hand side what do we have? Rho phi p 1, right, times delta V minus rho phi p 0 times delta V, right, that is all on the left hand side. Yes, okay. Then on the right hand side we have what do we have? We have f times, okay, I will just write down whatever we have written, okay, that is, yes, f times sigma, I would write down the same equation, okay, gamma grad phi 1 f dot af plus 1 minus f times sigma gamma grad phi 0 dot af times delta t, right, plus we have f times SC plus SP phi p 0 times delta V plus 1 minus f times SC plus SP phi p 1 times delta V times delta T. Is that correct? Oh, sorry, this should be 1 or none and this should be 0. Okay, 0, fine, 1 and 0. Is that correct otherwise? Okay, yeah. Now this gamma grad phi dot af would give rise to what terms? Phi east minus phi p phi naught minus phi p and so on, right. Essentially you would get all your A east, A west, A north, A south from these quantities as well as the second one, that is 1 minus f, right. So, you would get from here as well as from here. Okay. Then let me divide everything with delta t, okay. Let me divide everything with delta t and collect the terms for the coefficient phi p on the left hand side, okay, because we always want coefficients of phi p on the left hand side, right, even when we had the diffusion equation alone. So, and also divide everything with delta t. So, what will be the coefficients on the left hand side for phi p? First term is of course this guy, rho delta v divided by delta t, okay, that is first term. Now, where do you get other terms from for phi p? So, phi p is what, phi p 1, right. Which terms can contribute to that? Can the first term contribute, this one? Yes, it will, right. What about the second term? It will not. What about the third term? Yes. Fourth term? No. Okay, then let us consider these two and then can you tell me what will be that? From the first term you would of course get sigma A and B phi p, right, because you will get A east phi east and then you have another term which is A east phi p, right, which will be sent to the other side. So, similarly you have all other terms, right. So, that will be, and they all come with a minus, right, when they go to the left hand side they will all become plus. So, this will be plus f times sigma A and B on all the faces times phi p, that is outside. Anything else that will come from the first term on the right hand side? Nothing, that is all, right. What about the third term? Which one will go into f sp delta v, right. We have already divided with delta t. So, this will be plus or minus? Minus, right. This will be minus f times sp delta v, that is all on the left hand side, right. So, we have successfully written phi p coefficient, right, correct, or any other term would contribute, that is all, nothing else. Okay. On the right hand side what do we have? Right hand side of course from the first term, if I were to calculate what is from the first term on the right hand side, what will be there? F times sigma A and B, phi and B, these are all 1, right, these are all calculated 1, okay, plus what else? From the second term you will have, how many terms will you have from the second term? Second term will have A east, phi west, all these things, and then will it also have phi p 0? It will have all those things, we cannot send it anywhere, right, because those are all unknowns or knowns? No, so they should stay on the right hand side, right. So, until we have now two set of terms coming from the second term on the right hand side, those are 1 minus f, right, times sigma A and B, phi and B 0, right. These are all the neighboring coefficients, and then what else we have? We have phi p, but that will that come with a plus or a minus? It will come with a minus. So, that will be minus 1 minus f times sigma A and B times how much? Phi p 0, right, because phi p 0 will have east, west, north, south, all of them clubbed, right. Do you see that? Okay. Then of course, we have this trailing term, right, we have this guy which is which we did not talk about on the left hand side, that also will come to the right hand side, right, because this is a known or unknown? Known. So, we will send that guy to the right hand side, that will be how much? That will be a plus rho delta v upon delta t times phi p 0, okay, fine. What else? Then we have a bunch of source terms that are coming from 0, right, as well as the SC of the 1 level, right, okay. Then let us put all of those together, that will be f times SC 1, right, plus 1 minus f times SC plus SP phi p 0, times delta V delta V. Is that correct? Anything else? That's all, right? That's all, okay. Fine. Anything did we miss out or no? Okay, fine. Yeah. SC1 is okay, SC1 is a good question. So, if we have so what will be SC1? It will be SC evaluated at phi at the previous at the current value, right, but you have to introduce a model for it. You have to, this will be evaluated at 0th level, right. So, whatever I have written as C1 actually corresponds to 0 only, right, because you would introduce phi star values for that SC, right. So, I would then drop this guy read SC, okay, and this is also, so this is basically known, right. That is why it is on the right hand side. So, I will write this as, I mean I will leave it as SC1, but you understand that this is actually a SC for the next level, which is evaluated using the current level values of phi. Okay, if you have a nonlinear variation of S that is dependent on phi, okay. SC will be the same actually, right. It could be, yeah, it will be just a constant. So, it will not be. So, it will be anyway constant. So, I do not need this one here, okay. That is basically not required, fine. SP could be a function of phi, right. As a result, I would need something there, fine. But SC and SP could be functions of space, which is fine, which is nothing to do with the time level, okay. Other questions? Okay, that is good. So, I would like to kind of rewrite it little bit such that we will kind of recognize it. So, I would like to write it as our old thing, that is AP phi P, okay, where AP is what? Everything that is in the curly braces equals F times, okay. So, I would like to write it as, we have phi and B coming here, what other phi and B's are here? So, we do not have any of the other things. So, this will be F times sigma A and B phi and B, right, that is what we have, plus we have a lot of terms here. Can I combine any of these things? Phi and B 0 is there, PP 0 is there, right. So, okay, then I would write it as I will call this term as sum AP 0 because it is multiplying phi P 0, okay. So, we have that term. So, that means I have plus phi P 0. Can we collect the terms for phi P 0 on the right hand side? What will be there for phi P 0? This AP 0 that I just wrote plus, yeah, SP is there, and then you have this guy, right, that would be plus 1 minus F times SP delta V, right, coming from here. I am multiplying with collecting terms of phi P 0, okay. Minus or plus? Above would be minus 1 minus F times sigma A and B, right, that is what we have, yes. Okay, no, it should be fine because we do not have, yeah, I mean AP 0 is something that is coefficient of phi P 0, that is all. We do not have zeros and ones for the coefficients anyway, right, these are, unless you have a different notation, right. So, AP and AP 0 essentially reloads another constant that is multiplying phi P 0, that is all, fine. What else is remaining? What else is remaining is basically the phi and B zeros. So, that is plus 1 minus F times sigma A and B phi and B 0, right. plus this entire thing, which we would call it as some B term, right. That is basically f times SC plus 1 minus f times SC times delta V, right. Is that what we have? Fine. This should be just SC delta V, isn't it? If we choose some f here. So, did we get the AP Phi P equals sigma NB Phi NB plus B? We have got it, right. I think this is the working equation now. Is this fine? Okay. Now, in the next lecture, we will see how to obtain different time stepping schemes by setting different values for f. Okay. That is what we will see in the next lecture. As of now, this is the general equation for any time stepping scheme. Okay. Thank you.